Good afternoon. Welcome to CERIAS Security Seminar. It's my pleasure to introduce today's speaker, Meng Xu. Meng is a fifth-year PhD student at Georgia Tech, advised by Professor Tae-So Kim. His research interests are in software security, version programming, and bug finding. He has published many papers in top security conferences. And in fact, even as a PhD student, he has served on the program committee of ACM CCS conference. So today, Meng will talk about bug finding in OS kernels.
So thank you, Ninghui, for the introduction, and thank you for inviting me here for the talk, and also thank you for the waiting. It's been the Mac has had some issues, but hopefully it's fixed. So today I'll be talking about some PhD work I have done, like during my years in Georgia Tech. So some little bit about myself. So I'm starting my fifth year PhD at Georgia Tech. My advisor is Tae-So Kim, and I have collaborations with Wenke Lee, Michael Bacars, and Marcus Pinello from MSR through the internships. So as some background on my research experience, so the first year I was pretty much enjoying it as a freshman. So I did a survey on the Android securities, which is published in ACM CSUR. And also I did some work on browser privacy issues in see whether the browser implemented this incognito and guest mode correctly, and was published in CCS 15. So if you're interested, feel free to talk to me afterwards. So in the second year and third year, I was mainly into the theme of this software diversity. So the main argument is like this: the whole computer monoculture makes attacks very easy, because as long as you know what the target victim is running on, you can profile it, run all the kind of experiment on your own, and then you shoot the packet to exploit it, and done. You can exploit millions of machines. So what can we do to solve these issues? And we resort to the software diversity part. And for that, we have two works lining up. One is like, how do we fuse these compile time diversification schemes and run them concurrently at the same time? And the other work is how do we use different operating system or platform diversity to detect PDF malwares. So if we go a little bit more details on this, so this fusing the compile time diversification things is showing on the left. It's the Bornstein work published in ATC 17. So basically, it's a framework that you can run multiple program variants at the same time. So and the key to this architecture is the recording system, which or the synchronization system, which one variant will actually trap into the kernel, dump the information into, in this picture, a ring buffer, and then the other variants, or we call the followers, which is instrumented with different sanitizers, will come in and then compare with what already have there in the kernel, in the ring buffer. And if we see any divergence in the execution, we call this as a alarm, and we raise the alarm and saying that, hey, something is going wrong. Maybe one of your variant is exploited or is under attack. Please do some investigation. So in terms of this OS diversity or platform diversity, it was published in Userspace Security 17. So it was summarized by the picture on the right. Basically, we send the same PDF file into two platforms, one running on Windows, the other running on macOS. And then by comparing the internal external traces, we know that whether this PDF is a good one or a bad one, because the assumption is that if a good PDF, it should behave exactly the same on the two platforms. Otherwise, if it's trying to exploit something, very likely it will fail in one of the platforms. And in our cases, most attacks fail in macOS because they are designed with Windows in mind. So this is another way of another aspect of trying to detect malicious PDF documents. So my fourth year is more towards the bug finding applications. And also I do some internships in Facebook and Microsoft Research, just to know how the industry is conducting the researchers. So if you're interested in my experience there, you can also talk to me offline. So today I'll be talking about the bug finding work, which is about precise and scalable detection of double fetch bugs in the OS kernels. And this is work done with my colleague Chunxiong Qian, Professor Kangjie Lu, Michael Bacars, and my advisor Tae-So Kim. So what is a double fetch bug? And what is a double fetch in the first place? So this all happens because we have this address space separation in the modern OS design. So basically, for any kind of application, you have the user space or the program space and the kernel address space, and they are totally separated. For the user space, for the user program, there's no way you can access the kernel space directly, but the kernel can access the user space. Now, if you want to say you want to tell the kernel to do something, then you're going to give kernel a pointer which point to your own address space. In this case, you try to invoke this kernel function, and your user space pointer point to some struct called deadbeef, and so the kernel is not going to directly dereference the user space memory because it might not exist, it might cause fault, and if that happens, the kernel crashes, and we don't want that. So what the kernel will do is that it will try to first copy your address, your memory, into the kernel space memory. In this case, you're going to first copy this deadbeef, this 4 bytes, into your kernel memory and do whatever things on that. And basically, it's transferring this user space pointer into a kernel space pointer. And there's some guidelines in terms of how you can do this user space pointer copying. So the first thing that you shouldn't do the direct dereference. You shouldn't do this star k pointer equals to star u pointer, because this directly dereferencing the user space pointer might cause a kernel panic if the pointer is not there or is pointing to the wrong address. So what you should do is you should use this transfer functions. Like in this case, it's called copy from user. So basically, you tell the kernel that, hey, I want to copy the u pointer into k pointer for 4 bytes. And this is the correct way to do. And every kernel to user space accesses has to be fall into this pattern. And there are three user space copying functions. One is called copy from user, the other called get user, and the third one called memdupe user. So all of them these are the only 3 mechanisms you can try to access user space memory. And this gives you a clear indication that, hey, this kernel is trying to access something in the user space. Now, there's another implication that why this deadbeef, the structure resides in the user space, address space, is there could be multiple threads running at the same time. So in case that one thread is trapped into the syscall and try to invoke this k function, there could be another thread trying to access this structure at the same time, which means that if you copy something into the kernel and sometimes later the other thread try to override the same address, the content could be different and there could be some inconsistencies. And this is the root cause of the double fetch bug, which we'll show you later. So now we understand why we do a single fetch, because now the things resides in the user space and we want to bring it into the kernel space. Now, why do we do double fetches? It's very similar. It's very simple. It's now the reason we do single fetch is we know the pointer is going to be pointing to a 4-byte structure or 4-byte data. But in some cases, we don't know how large is the total message. Therefore, what the kernel and the user space developer agree on is that the pointer is still pointing to something, and this time we're going to say that the first 4 byte of the structure is going to contain the actual size of the whole structure. So which means that we don't care. So we don't have to pass an extra argument to the kernel saying that this is a 30-byte struct. We are going to just pass the pointer, and you first fetch the first 4 byte, dereference it, get the total size of the struct, and then copy it again. And this is exactly what happens in the kernel. So for example, you have a user space pointer pointing to it, and you first fetch, you get the first 4 byte only, and you dereference it into 30. And later you're going to do some sanity check, because you don't want this thing to be ridiculously large or ridiculously small. So you have to do some sanity check, make sure that it's within a given range. And in this case, definitely 30 seems to be a good number. So you'll pass the sanity check, and you'll go to the next. Okay, you pass the sanity check, you know that the whole structure is going to be 30 bytes. And then you know that next time you do the fetch, you are going to fetch the whole 30 bytes message into the kernel. Now, this is why we call it a double fetch. Now, if you think carefully, what could go wrong in this whole process? Now, it's once you, no, it's like still you first copy the 4 bytes into the kernel space, and recall that we have a user space other thread trying to access the same memory. Now, after you do the first fetch, and while you are doing the sanity checks, there could be another user space thread trying to override the first 4 bytes of the memory. And in this case, we could simply override the first 4 bytes into a ridiculously large number, 64K in this case. And because you don't know this, you're still going to copy the same from the same address and this 30 bytes, and then next time you get this whole structure, but you don't know that the first 4 bytes of the whole structure has been changed. And later, if you do some processing on this structure, and then you do some processing on this UATTR in this case, you do processing, you receive a result, and then you now want to copy the result back into the user space. Now you are going to ask how many bytes I should copy back, and then you look for the first 4 bytes of the struct, and then you find that, okay, I need to copy 64K kilobytes of address of the kernel space into user space, and then you have a kernel information leak, because there's no way you have this 64 kilobytes of buffer, and definitely you're going to leak other processors information and probably some keys, some data, anything you want. So this is how this double fetch bug can lead to serious exploits. Now, why this double fetch pattern is so prevalent in kernel? What you just see is they're trying to do some size checking. So we want to ensure that the size is within a certain range. It's not too big or too small. And there could be other cases, for example, dependency lookup, protocol signature checking, or some information guessing, because the information given by the user space is not complete. So I'll show you several examples. So this is an example. This is a case of dependency lookup. So what you're trying to do is you're trying to first get the message header, similar to the size thing, you get the first few bytes. And then from the header, you try to see whether there's you try to get this IOC number, which is a device number. Think about it as a device number. And then you try to look up whether there is a device in the kernel to handle this request. And if there is a device, lock to handle the request, release the lock, and give up the device. So this is what intended by the developer. But what actually you can do is because you can change after the first fetch, what you can essentially do is you can ask the kernel to hold the lock for the number 1 device and do this download using number 2's resources, and then release the lock for number 1. And if you do this kind of attack, you can do mutual kernel deadlocking, or you can use some risk condition, because now this do FW download function is not protected with any lock. You can do all kind of data races with it, and how you want to exploit is it's up to your imagination actually. And this is another simple attack. The kernel try to enforce that you shouldn't send out messages, which is not TLS version 1.2. And so what they do is they fetch the header first and quickly check if this version TLS 1.2. If it's yes, then go ahead. Otherwise, reject. Now, the intention is very good, so we don't need to copy the whole message to know the header. But what actually can happen is you can you can give it a TLS 1.2 version just to spoof the protocol check. And after you do the second fetch, you can change it to whatever TLS version you want. And this kind of break down the assumption that you cannot send out messages not in TLS version 1.2. And there's some prior works that try to detect this kind of bugs. So the Botch Spawn project is what codenamed this bug as a double fetch bug. So they try to run on Windows kernels and try to use some dynamic analysis approaches. Basically, it forks up a virtual machine, and then try to send the syscalls, and then it try to monitor whether there are 2 consecutive memory accesses to the same memory. And if there's yes, then possibly this is a double fetch bug. And then they report this to the user, and up to the user to manually check whether this is actually a bug or not. And also there's a work called decaf, which also falls into the lines of dynamic analysis, but instead of working on Windows, they work on Linux. And instead of using a virtual machine, they try to use this cache side channel. Because if you're consecutively accessing the same memory addresses, the cache is warm, and it takes very small amount of time to get it. So they exploit this side channel to get the timing information, and it's much more clean than this virtual machine inspection scheme. And also there's also another work which falls into the static analysis one, which is Pengfei's work on Userspace security last year. So it tried to do some lexical code matchings. So basically, it kind of defined a pattern in a code, saying that if I see the code written in this way, say the two variables are the same name and they are involved in this copy from user and get user functions, and then we consider this could be a double fetch bug, and then we go to manual inspection to do that. So the good thing about the static scheme, which means you don't need to actually execute code, is like they have very high code coverage. You can possibly cover all the kernel code, even without the actual hardware to support it. But the thing is like has a lot of false positives, false negatives, because you can't possibly precisely model all the executions. Also, the dynamic scheme is on the contrary, so you have very precise information about when this memory is accessed, but you cannot possibly run those drivers without hardware support. So what we try to do here is not much different from the Pengfei's work that falls into the static analysis. But the major difference is like instead of using lexical code pattern matching, we try to define this symbolically or in a more systematic manner, which in the later talk you will see. And because we have this much more precise definition, we can have both high code coverage and also precise detection. So basically, how do we define a double fetch bug? So we define the double fetch bug by defining what is a fetch. So a fetch is very simple. It's just a pair of two variables, symbolic variables, address and size. So address is the starting address of the fetch, and then size is how many bytes is copied in the kernel. So they are symbolic in a way that it could be concrete numbers, or they could be like a symbolic number, which depends on user input. We just don't know. So then we define an overlap fetch. It's like two fetches are trying to access the same part of memory, or at least some partial of them are overlap, which can be further visualized in this way. So if you have a get user and then copy from user, which falls into this pattern, and then we think that this is clearly an overlap fetch, because this ATTR part is actually fetched twice into the kernel space. And also another common pattern you see is like you first fetch the header of the message, which is usually in the form of size of struct header, and then you dereference the size and you do some calculation and you derive what the size of the whole message. And then next time you copy from user the whole message. So these are the two most common patterns we see when you do this overlap fetch in kernel. And now we have overlap fetch, but not every overlap fetch is actually a bug, because like it's, for example, if I after the second fetch actually do some check to ensure that the overlap regions are the same, then this is not a bug. So how do we formally define that whether this is a double fetch or a double fetch bug? We resort to this like control dependence and data dependence definition. So if we call this a bug, if either control dependence or data dependence can be established, and we cannot prove that those overlap region doesn't change during the two processes. So a control dependence is like some variable must satisfy certain constraints before the second fetch can happen. So in this TLS case, we have to say that in order for the second fetch to happen, this header dot version has to be TLS 1.2, otherwise it's a return E not supported. So therefore, we kind of implicitly imply the constraint that in order for the second fetch to happen, this shared variable has to be this. But after the second fetch, we didn't further check that this full dot version has to be TLS 1.2 version. And therefore, we conclude that this is a double fetch bug. And also in terms of dependency, data dependency is like that. So control dependency is like you have the overlap region affect the control flow. And then the data dependencies is like the overlap region. You somehow use the data inside it to derive something. And in this example, you try to use the IOS control number to derive the actual device controller or device adapter to acquire the lock and to do this download functions, which kind of form a data dependency. But after you do the second fetch, you didn't even further check whether this number are the same, and then therefore we conclude that this is a double fetch bug. And also, there could be cases like you have both control and data dependencies, and there will definitely be a bug as well. So to quick recap, in order to call something a double fetch bug, we have to say that they copy from the same user space memory that covers somehow overlap regions, and they have to establish the control or data dependence. And furthermore, we cannot prove that after you do the second fetch and until the end of somehow the function, we cannot say that the overlapped memories are the same. And then if all the conditions are satisfied, we call this a double fetch bug. And this is way better than trying to define the code pattern that this variable is used here and then used there. And in this way, it's more precise and so more convincing to convince like both us and the developer that, hey, this is a bug. So how do we find those things according to the definition? So basically, we try to find as many as double fetch pairs and construct those code passes that go through both pairs. And then we're going to symbolically check each of the path to see whether this path makes a bug or not. So basically, how do we collect the pairs? So we try to statically enumerate all of them that could possibly occur. And the ideal solution is like, okay, we are going to identify all the fetches in the kernel, and we are going to construct a super big, complete interprocedural CFGs. And then with that, we can do pairwise reachability test. But the second and third point is almost impossible to be done, just because the kernel is way more complex than we can think. Therefore, we do try to do this in a bottom-up way. So I'll show you with an example. So how do we do this bottom-up fetch pair collection? So we start from one fetch, and within its function, we try to look upward. So we search through all the instructions that could possibly reach this fetch. And in the first case, we get very lucky. We find another fetch. And good, we get this fetch pair. If in another case, we see that a function is called, and we know that inside this function, there's a fetch somewhere. And what we do is like, we're going to inline this function and then make this whole enclosing function like containing two fetches again. In the worst case that we couldn't find anything, so we just conclude that this is not a double fetch. I mean, this enclosing function doesn't give you a double fetch. And therefore, we don't check these things. So now we have the fetch pairs and we have the code paths. Now the next step is like, how do we symbolically check each of the code paths and to determine whether this is actually a bug or not. So basically, the goal of this symbolic checking is to symbolically execute all the instructions over there and to see whether the two fetches satisfy the definition we just said, like there's an overlap. And you have to either have control or data dependence, and we cannot prove that this overlap region are the same after the second fetch. So let me show you with an example of how this is done. So this is actually the case of this perf event, which is it's a little bit simplified, but it shows you how this is actually done in a actual code. So this is the function that has a double fetch we just see. And so how do we do symbolic checking? Now, at the beginning of this function, we immediately know something. For example, this uattr is a pointer that points to some user space memory. And this attr is a kernel space pointer, which points to some kernel space memory. So we're just going to annotate those things with $0, $1, and @0, @1, just to represent that these are pointers and pointing to some memories, and one in user space, one in kernel space. So then we go down to the statements. So when we see the first fetch, we are going to say that the first fetch is a fetch pair A and S, and the address is the UATTR plus 4, and size is 4, because get user will get the same size as the first variable. The first variable is a U32 integer, so it's 4 bytes. So we immediately know that this first fetch, how to represent this first fetch. And later we do some sanity checks, which is basically assert some constraints on this $number 2, which represent this size variable. And after the second fetch, we're going to do after the sanity checks, we're going to do the second fetch. And in this time, we get a constraint that the second fetch starts from 0, which represents UATTR, and the size is a symbolic expression. It's $2, and $2 is what you get in your first fetch. And after we do this, now when we reach the end of the function, now it's time to check whether this is a bug or not. So we first try to see whether this is an overlapped fetch, and it turns out yes, it is an overlap fetch. So because we could have a size, say like 7 or 8, that covers that is, as long as it is more than the 4, and also satisfy this page size and the perf attribute size version 0 constraints, we can possibly have an overlap fetch. And the next thing is like we are going to check whether this makes it a double fetch bug or not. So basically, we are going to see whether this data dependence or control dependence, and in this case, we have both dependencies. And then we think that this could be a bug, and we are going to check whether at the end of the function we can ensure that this the same thing that copies in the two fetches are the same, which in this case is the size and also this attribute point size. So, and we send this constraint to the solver, and the solver says that there's no constraint that has to force them to be the same, and which is true. And in this case, we conclude that this is a potential double fetch bug. And we report this to the developer, and the developer acknowledged and patched it. So, and in the paper, there's a much more like advanced example showing you 2 more features we can do. Like we can do some loop unrolling, and also we can do some pointer resolving, like alias analysis thing, just within the context of what we are going to analyze. So if you're interested, I'll refer you to the paper, which is in Auckland this year. So in findings, we find 24 bugs in total. Like 23 of them are in the Linux kernel and 1 in the FreeBSD kernel. So 9 bugs has been patched with exactly the patch we provided, and 4 of them are acknowledged, but like the developer think there's going to be some major restructuring, so they are wait for further like integration into the kernel. And there are 9 bugs are still reviewing, and 2 bugs are interesting. So the mark has won't fix specifically by the developer. And the one case is like the developer think that this is a risk condition, but it's not going to be causing any serious issues. It might mess up with the internal state, but there's no visible thing you can do. So they are not going to fix it. Okay, fine. The other bug is actually a false positive from our system. So if you recall that our system requires a enclosing function, and the assumption is like at the end of this function, we cannot assure. I mean, once you get out of this function, there is no way we can assure that these overlap regions are the same. But in that particular case, they can assure, and they actually do assure this outside that function. The reason is like they return 2 things out. One, the actual size return with the return, and the other side return with a pointer. So they actually do pass out both information, and they do the check outside that function. So this is another case we cannot. This is false positive, and this is a case we cannot handle. So, but this enclosing function design actually simplifies this symbolic checking and actually enabled everything. So we're going to pay with this false positive. So next thing is how do we mitigate this kind of bugs? So the basic idea is to reassure that the control and data dependence between the 2 fetches are the same, like to just reinsure this. So in other words, we try to do this syscall automatic, atomicity. Yeah. So basically, there are 4 patterns we can apply to patch this kind of bugs. The first one is like we are going to override the second fetch, which means that however you fetch in the second time, we are going to override the same memory with what you get in the first time. Now the second way to patch it is like instead of we override, we are going to detect whether you have changed something or not. And if we detect the change, we're going to early abort. Like in this case, return an invalid, go to E invalid. And the third way is to refactor this overlap fetches into incremental ones. For example, I don't in first fetch I copy the first 4 bytes, but in the next fetch I skip the first 4 bytes and I copy start from the rest. And then internally I merge them into a very big structure. So this is the third way of refactoring the fetches. And the last way is to like refactor into a single fetch, and this is usually very complicated, and it requires some knowledge of how this is internally working and how we can further optimize the data structure. And this is not a generic enough way to patch it. So initially we try to send all the patches in this way, so because it is simple. But some developers don't like this. They want this to error abort, or they want to refactor into increment copies, or they want this kind of thing. So how really you patch it is totally up to the developer, like the kernel maintainers. So usually we don't have the way, but all of them should be able to mitigate this kind of attack. And we try to see whether there are like automatic ways so to do this, but seems like given the experience and the complexity of the kernel, there seems to be not very good way to automate this. Recently, the decaf work provide a promising solution. So it tried to use this Intel hardware called TSX. So it's basically lock all the syscalls into transactions. And if you do that, they automatically imply that when the memory you protected under the syscall, they cannot change. Otherwise, this transaction will abort, like database transactions. You cannot change things. So if this is definitely one way of doing this automatically, but one, it applies to Intel only. And second, even with this TSX thing, how do you handle this abort routine is another difficulty. So, and I don't think the kernel developer are going to implement, but this seems to be a promising approach as well. So some limitations of our system. So we couldn't handle this. Everything had to be compiled into LVM, so we couldn't handle those things. That cannot be compilable. So we have to, in terms of this constructing this execution paths, we have to limit the number in some sense. So luckily, like 99% of the path construction can be done within like 10 or 15 paths. So we set the limit to be 4K, so which in the hope that we could accommodate as many paths as possible. I think only like 200 or 300 functions like exceed this limit. The rest is totally fine. And also in terms of loop unrolling, we only unroll a loop once. So a better way could be like abstractly interpret the loop. So we can represent a way of unrolling the loop in any times. But for this work, we just limit to once. And also in terms of symbolic checking, we ignore most of the inline assemblies. Although there are not many of them, some of them do appear and cause some trouble. Although they don't cause false positives, but it could cause like false negatives. And we also have very imprecise pointer to object mapping. So remember that in the entry of the function, we are going to assume that these pointers point to different memory objects. And we hope that they point to, like those pointers have types. So we know that how much memory this object actually occupies. But these are very imprecise assumptions and could be invalid. And also like in the case of the one false positive, we could have wrong assumption on like what constitute this enclosing function. So in conclusion, we think that detecting double fetch bugs without a precise or formal definition has possibly led to many false alerts or tremendous manual effort. So in terms of more systematically detecting this, we try to come up with this this mathematical model or mathematical definition of what constitutes a double fetch bug, and then we try to find develop a system using this model. And by doing this, we believe we achieve both high accuracy and also high scalability. And we think that this double fetch bug doesn't apply to only kernels. It could apply to many other things as long as you have a function or privilege boundaries. For example, user space, kernel space, okay, that's a kernel. And then for hypervisors, you have the same boundary, access boundary. For browsers, for trusted execution environment, they could have double fetch bugs in those applications as well. And we hope that our scheme can also apply to them. I also think that apart from this memory safety bugs, buffer overflow, user free, the risk condition bugs are now pretty much more interesting. They're on the rise. We hope that we could find more of this kind of bugs in a modeled and systematic ways. So let's conclude my research on this, and I'll briefly show what I'm going to do next. So basically, I'm more into this bug finding thing. So very likely I'll try to make this detection more generic. So to try to find bugs and more bugs. So basically, what you just see is if you think this way, what you just see is a partial symbolic representation, which means that we are only representing a slice of the program into a symbolic way. In this case, we are only representing this simplified function into a symbolic manner. Now, and by doing that, we still can find bugs. And this actually means that if you do this kind of symbolic representation, finding bugs becomes as easy as writing the mathematical condition that this bug happens and send them to the solver. So this is kind of new way of trying to find these bugs in a more systematic and fancy ways. So what if we can do this whole program symbolic representation? So what if we not only model a function, but model a large chunk of a program? So what can you do? Can you find more interesting bugs or simply more bugs? So, and there are tons of issues or roadblockers along the line of research. For example, one key thing is how do you model this heap memory? And how do you handle those recursive data structures? For example, linked list. How are you going to represent them? And are you going to actually traverse the linked list? For symbolic execution, there could be millions of thousands of nodes. How do you do that? And how do you do this path explosion, avoid those, and or represent them in a more scalable way? So these are the PR community has come up with a lot of interesting techniques. For example, they try to assume this type safety in the heap memory. So basically, each object is in a type safe way, it's totally typed. And also, they come up with this segment offset and plain memory model, which use 3 indexes to represent a memory instead of one symbolic index. So they could be used to for this whole program representation. And also, in terms of this recursive data structures, there's a separation logic and byproduction from this PLDI. From the PR community, which we could use to represent those recursive data structures. And we can use some abstract interpretation to avoid the path explosion, or at least try to confine those in a way, or at least give the trade-off hey, if my path is going to be explored, I have a way of constrain it or abstract it, or at least I know what are the compromise I made. So, and along this line of research, we have been working on trying to represent the Linux kernel drivers. So the reason we chose them, first thing, there are many of them. There are more than 4,000 in the kernel. And most of them are rarely tested because they don't have the hardware to test it. And each driver, and although it's the kernel is a huge thing, each driver is pretty much self-contained. So it's small application which, scaling the thing to the whole kernel might not be possible, but if you get the driver models and then only simulate the single driver, that could be doable. And also, this is definitely challenging enough for the symbolic executor, so that's why we choose them. And so the plan is like we're going to symbolically execute this initialization function of the driver. So once you symbolically do that, it will give you a memory map. It will give you two things. So one thing is like the point to graph. So basically it gives you a thing like, hey, this pointer is pointing to potentially this number of memories with this set of constraints. And then they give you the call graph, like with all the function pointers resolved. And this is the benefit of having this init function. So once you have that, we could have like the next thing is to find bugs. And then finding bugs, it becomes a search problem. So given this memory snapshot and given all the possible function calls or function traces, so how do you combine them and to find the bugs? So this is the search space problem. And what we're trying to do is we try to do this multi-dimensional symbolic checking. So the very naive way is like we have a snapshot of the memory model, and then we send them to one set of function calls, and see whether there's any issues in this. So in the first case, we could find like, hey, the driver's abort procedure call might have a memory safety issue, just by like symbolically traversing all the possible function calls. On the other hand, we could find like, hey, this driver's close procedure doesn't have any issue. So this is like per procedure check. So what we could possibly do is we could possibly start to organize the things, because if you are familiar with the drivers, each driver doesn't operate in a single snapshot, in a single like one-shot thing. It operates in a sequential manner. So it could be possible like we could first open the driver, then do something, and then abort, and then close. And if we do this, there could be a bug. Otherwise, there couldn't be. So can we find this kind of things that depends on how you invoke the driver? Can we find this kind of bugs? So this is another thing we are looking at, which is called sequential checks. So the last piece of this multi-dimensional symbolic checking is like we could do concurrent execution on concurrent checks. So the bug, like say there's a data risk, and it will only happen if you given this snapshot, if you run these two functions concurrently, and see if you one process is calling this abort, the other process is calling the close call. So there could be a risk condition inside this call sequence, and then whether we can find those bugs by doing this concurrent check. Now what if the search space is too huge for symbolic execution, because we're talking about solving constraints here? Now we have fuzzing. So if we couldn't solve them with all with the state-of-the-art constraint solver, or simply there are too many, we're going to rely on fuzzing to systematically explore the search space. So basically, it's the same picture. Instead of like trying to solve everything, we're going to randomly generate the inputs and see if any of them cause abnormal behaviors like crash, or in file systems, inconsistent state on the disk. And similarly, we can do this per procedure, or in a sequential way, or in a concurrent way. So like we couldn't solve this with symbolic execution, there's fuzzing to support this. And also, since I gave some information on this diversity thing, like software diversity, I believe that it has like much more to offer than what we just described just now. So if we think about the diversity procedure, it's like, hey, if I'm going to run some, say, PHP applications, there could be many possible ways to put the diversity in. So I could do at the process level. So say I could instrument this PHP interpreter with different sanitizers or different diversification schemes, for example, like layout randomizations or stack paddings. So this is one way, and this is down called process level. And there's another level, which is called implementation level. Say there are tons of PHP interpreters. Like the Zend is the official one, but there's HHVM from Facebook, and there's JPHP written like in Java. So they are completely independent and developed by different group of people. So what if we send them the same PHP script and see their results, whether there are different results coming up? And if there are different results coming up, does it mean that any of this interpreter is vulnerable? So this is another angle we could look at. And the last part is the platform, like the OS you runs on. Like the example we show you, the PDF malware detection. So it actually leveraged like the exploit couldn't possibly exploit both Windows and Mac OS. Now, same thing, we could have a PHP exploit that couldn't exploit both Linux, like all of it in Linux, Windows, and Mac OS. So these are the 3 layers of diversity. And if you think like along this line, the first and the process layer and the OS layer has been done by the 2 work, and the one in the middle, there's something we can do. And also, not only like we can run with the user space applications. So we could run with like drone systems, which has this real-time constraints. And what can we do on top of these things? For example, the drone system has a lot of drivers. And the driver code can also potentially apply all these kind of diversification techniques. So can we do something over there? And the last thing is like, can we combine this like synchronization and mismatch with fuzzing? So right now, fuzzing only gives you like signals if the thing crashes and you get a call dump. But what if there's a data leak? Possibly you would let the leak happen because the program doesn't crash. Now with this kind of diversity and synchronized execution and combined with fuzzing, we could possibly detect those uninitialized reads or data read or data races even. So I'm also like interested in red teaming against this verified software. So the reason I get interested is like, so if you recall this symbolic checking thing, is more like symbolically proving that, hey, I don't have this kind of problem. Now this verified software is exactly along this line of research. So the developers are putting up the specifications saying that the software has to adhere to this, and then they are going to generate machine check proofs to ensure that their implementation is actually on par with the specification. So what can we do as a security researcher in line of this verified software? So are they going to be like widely adopted? So are there any security problems? Or are they going to be like missing specifications or even wrong specifications? Or are they actually free of bugs in terms of those unverified parts, like those libraries and like the interfaces? Are they going to be good? So we like to explore this for the SEL4 kernel, and then do a lot of more fun stuff on top of it. So yeah, with that, I conclude the talk, and thank you very much for your time.